Avani. Dude, come here. Can't have you stepping on this piece of paper. Um. So I don't actually do the copying myself. So what they're saying.
did I press? Shoot. Insert. I always forget. So we've got task schedule. Now, number one important thing to remember for me is watch the edge cases and make sure that I'm doing. So let's do this. Charge this for a little bit. Alright. Task scheduler. You're given an array of CPU tasks, each labeled from the letter A to Z. I'm gonna actually... You're given an array of CPU tasks, each labeled with letter A to Z, and a number n. Each CPU interval can be idle or allow the completion of one task. Task can be completed in any order, but there's a constraint. There has to be a gap of at least n intervals between two tasks of the same label. So return the minimum number of CPU intervals required to complete all tasks. So if we're given the inputs A, and then B, and our n is equal to 2. What it says, so each letter will be labeled A to Z. I'm assuming all these letters are going to be capital letters. I assume that n will be less than the length of tasks. Doesn't look like it. But that's maybe not a huge deal. You're given a array. Each label from the letter A to Z. Let's set a timer on this. And let's pause the music. So each label from the letter A to Z and a number n. Each CPU interval can be idle to allow the completion of one task. It can either be idle or it allows the completion of a task. Okay. So tasks can be completed in any order, but there is a constraint. There has to be a gap of at least n intervals between two tasks with the same level. So what it looks like is we could add A, process this, and then we gotta skip 2. So what it says, task can be, but there has to be a gap of at least n intervals. So this would, n is two intervals, and then we add B. Oh, we add. Yeah, okay, so we add A, then we add B, but then we gotta wait 2 intervals. There's nothing left here, so then why does it go to this next one idle? Oh, I see what it's saying. So what it's saying is each letter we add will be a clock cycle, right? So we'll add A, that's a clock cycle. We can't add another A because 2 more clock cycles have not been added. So we add a B. And then neither A or B can add it because there's been a clock cycle. And then we make this idle because there's nothing we can add. Then we can add another A. We can't add a B yet. Now we can add a B. This would be idle. And then we finish it off with A and B. Alright, and so this would be 1, 2, 3, 4, 5, 6, 7, 8, 9. This would be 9. But maybe I don't. 1, 2, 3, 4, 5, 6, 7, 8. 8. My bad. So this would be 8. But what happens if these are different letters, right? Let's say there's only two B's. Could we do something better than just starting at A? Because if it's A, what it would be is AB idle, and then we'd probably do AB idle, and then what? Then we get another A. Can we do better than this? I think so. So like what if we started with the smallest amount? So it would be B, A, idle, B, A, idle, and then we got to go idle again for A. So that's actually not the best. So it seems like we need to choose the one that's the most frequent. What's kind of going on in my mind right now is we could have a dictionary that keeps track of the count of all of these. So an initial for loop to get the count of all these. So A would be equal to 3 and B would be equal to 2. And then what we want to do is select the one that's most frequent that we're also able to select. Because, right, it doesn't have to just be A, B, A, B. It could be, like, if n is equal to 1, then this doesn't really matter. Alright. So, in my mind, how can I do this? I think having a count will be useful, but we also need to know what we can do next. So what I'm thinking of is maybe a queue could be really useful. So let's say this. I was thinking maybe a heap, but I don't know how useful that would be. But I definitely think we want to start with the largest element first, right? Whichever element has the most number. And let's say we started with A first. And let's say we add it to a queue, A. We know that we can't add let's see. So we know that we can't add another A for 2 cycles, right? So maybe we could have a position of when we could add A again. So like let's say here. And then we add a B. This is the soonest time we can add B again. And then each time we pop, okay, we can't add any element. Hello, Haley. I'm streaming.
I'm about to have my meeting.
All right.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem task scheduler. One of you suggested this problem, and I think it's a pretty good one. So we're given an array of tasks. It's a character array, and it's going to be limited to the characters from uppercase A to uppercase Z. So 26 characters. Each of the characters represents a task, and the task is something that the CPU needs to process. And the tasks could be processed in any order. Each task takes exactly 1 unit of time to process, so that's good because it makes things simple for us. And for each unit of time, the CPU could either process an entire task, or it could be idle. And the reason it would be idle is because we're also given non-negative integer input n that represents the cooldown period between the two same tasks. And the same task is represented by the same letter, the same character, in the array. And to understand this, let's take a look at an example. And by the way, what we actually want to return is the minimum number of units of time that the CPU will take to finish all of the tasks. Let's take a look at this example. We're given these tasks, right? 3 A tasks and 3 B tasks, and the idle time we're given is 2 units of time. So basically, let's say we processed an A task, right? That takes us 1 unit of time to process. Now we process a B task. And now we know that before we process another A task, we have to wait 2 units of time. So, let's say we process an A. We can't process another A. We have to wait 2 units of time before we can process another A. So what are we going to do in the meantime? Well, there's a B as well. So let's process one of the Bs. And now for this B, we know we actually have to wait 2 units of time before we can process another B. So the next time we can process another B will be at this point in time after we have processed our second A. So now the question is, can we fill this spot with anything, or are we going to have to be idle at this point in time? And there aren't any other characters, right? We had 1 A and 1 B. Now we have 2 A's and 2 B's remaining, so we can't do anything. This has to be idle. We process an A, a second A, and a second B. That means that before we can process another A is going to be 2 units of time. So this B, and then another unit of time, and then another A. And we also process a B. The next time we can process a B will be at this point in time. So at this point, again, we are going to have to be idle. But the good thing is that this is the entire, all the tasks we were looking for, 3 A's and 3 B's. So as you can see, it took us 1, 2, 3, 4, 5, 6, 7, 8 units of time to do this. So our output is going to be 8. So now let's think about a general approach that we could come up with to solve this problem. So let's say we had this as our input. First thing to notice is we're going to be given characters A through Z. It doesn't really make sense to worry about which character we're looking at, right? There's really not a big difference between a B and a C, but we should keep track of how many of each character there is. So we know there's 3 A's, 2 B's, and 2 C's, right? We don't even have to worry about the characters anymore. We can just focus on the numbers. We know that there's 3 of one character, there's 2 of a different character, and then 2 of another character. We know that the idle time in this case is 1. What order should we process the characters in? It's probably better to process the more frequent character first, the more frequent task first, because we know there's going to be some idle time, and processing the more frequent one first basically gives us more time to not be idle. And I'll show you the intuition behind that. Let's say we did a C first, right? We do C, we know that idle time is just 1, right? So then let's say we do B, and we're allowed to do another C right away. Let's say we do that, right? We do another C, and then we do another B because the idle time is only 1, right? So now we've already processed all the C's and the B's, and all we're left with is 3 A's. Okay, let's process one of the A's. Okay, great. But now we have an idle time. We have no other characters available for us, so we have to wait, and then we can process another A, and then we wait, and then process another A. So in this case, this was one way, but did this minimize the total time that it took us to process all the tasks? A different way would have been to start with the most frequent character, right? A, and now there's only 2 A's left. So now what's the most frequent? Well, you could say A again, but we know that there is an idle time of at least 1. So at this point in time, A is not available to us. So we have to process a different character, let's say a B. Then A is actually going to be available for us again, so we could process the A, or we could process the C. In this case, it doesn't really make any difference because there's 2 of each of these, so we could do either one. Let's just do C. So then there will be 2 A's, 1 B, and 1 C. Then we'll, of course, want to do the more frequent character, the A. And then there's going to be 1 A remaining. We can't process another A without at least 1 unit of idle time, so let's do B, and then do C, and then we can do A, right? This also is a valid way, and this one actually minimizes the idle time rather than this one. And what is the idle time in this case? It's about, not the idle time, the total time in this case is about 7 as opposed to 9 in the other case. So that's kind of the intuition why we're going to try to do the more frequent task first, and then the less frequent task. How we're going to be doing this is by using a data structure called a max heap, which will allow us to continuously figure out which task is the most frequent one. And the max heap can actually allow us to determine that in log n time, right? If we have a bunch of these, we can figure out which is the most frequent in log n time, which is good. But in this case, actually, it's even better than that. It's about log 26 since we only have 26 different characters. This is kind of a constant time operation anyway. But I will say that the overall time complexity is still going to be big O of n. One, because we are going to have to count the occurrences of each task. So we're going to have to go through the entire input, and we're going to be popping every value from our max heap and adding every value to our max heap. So the time complexity is going to be big O of n. That's also going to be the memory complexity. But now to the actual algorithm itself, we're actually going to use one other data structure, a queue. It's not required, but I think it makes the problem a little bit more organized. So let's start off with the max heap, right? We have 3 integers. We're going to be adding integers to our max heap, not the characters. We're going to be taking the counts of each task and adding that to the max heap. So we're going to have a 3 and a 2 and another 2. And by the way, when I actually code this up in Python, we don't have a native max heap. So the way we only have a min heap. In this case, we're going to change the count from being going to be adding 1 to the current point in time. We are but we're also going to add it back to our max heap, right? What's the idle time that is going to be remaining? Well, right now we're at time equals 1, and our idle time for each task is n equals 1. So basically, we're going to take n and add it to our current time. So it's going to be 2. Basically, at time equals 2, this task is going to be available for us to add to the heap again. So that's what the second value in this case means. And once again, we're going to pop from our max heap. We're going to pop the -2, and that means we have processed the task. So now our time is actually going to be time equals 2. We're going to take that task. It was a -2. We're going to add 1 to it, which is going to make it a -1. So then we're going to take that -1 and add it to our queue. And at what time is that task going to be available to add back to our max heap? Well, it's going to be 2 plus 1 because n is 1 in our case. So at time equals 3, this task can be added.
So that is what I missed. I missed the fact that in the queue I could keep, so I don't need a double into queue. I just need a queue. And this will be first in, first out. Yeah, so it's still a double-ended queue. Yeah. So what I do in the double-ended queue is I keep track of the time. I don't immediately add it back to the stack. I add it back to the max heap when the top element is available. Okay? And that is how we do it. So, and we're going to say while tasks left. We do the following, ... And then we have a count, the number of intervals is equal to 0. And what we'll do is return the number of intervals. My intuition was so close, so close. Now, in Python, our heap data structure will be heap queue. This allows us to create a heap. We're going to have a variable max heap, and then we need to heapify this. So this will be our max heap. And then we have while tasks. So while task is true, we'll need to keep looping. That's fine. Okay, that makes sense. And for every single iteration, we just increment the number of intervals. Okay. Now, so what do we do? Well, before this, we need to add everything to our max heap. And what we can do is set our num intervals to be there. And then what we can do is for key value in tasks left, what will we do? We'll add that to our heap. Heap queue dot heap push onto our max heap. And in Python, the heap that heapify gives us is a min heap. And the easiest way to make this a max heap is just put the negative of the number. I'm kind of proud of myself. I should have trusted my intuition more. I gotta trust. So we push our negative value, and then we also still want the key. That's cool. Now, when we get down here, we need to have another queue, a double-ended queue. And in Python, this is just dequeue. This will be a part of collections as well. And so what do? We take the top element from our heap. So the value, well, we'll say the count and the letter is equal to heap queue dot heap pop. All right, so I'm back. So we add all these to our heap, and so what I'm proposing is we have a counter variable, a counter dictionary that will be O of n time complexity, or O of n space complexity. A Q will be O of k space complexity, where k is this number. Technically, that's the n that they give us, but this is still greater. So still O of n space complexity. We'll have a heap, which will also be O of n space complexity. And we should have to do, I mean, basically just one O of n iteration through this. But like if we only have one character and then the gap is 2, then it would be n times k plus 1, right? So that's probably the biggest it can be. Now the k or n that they give us is relatively small, so it's less than 100, so we can just call this constant. So this would be O of n time complexity and O of n space complexity. All right, let's code this up. So we get our character, and what we want to do is we actually don't need to add it to an output array at all. We could, but I'm not going to. We just need to pop this, and then we add it. We add it to the left, and the reason why we add it to the left is that way we can get the top element on the double-ended queue when we want to. And what are we exactly adding left? We're adding in the value, or we're adding the letter. We're adding when we can add it again. So that would be the number intervals plus n. Because if we're at 0, right? And, well, the first thing we do is increment. So if we're at 0, we add it at position 1. So this is 0. This would be 1. So if n is equal to 2, when can we add this again? It's not 0 plus 2, it's 1 plus 2. It's at this third position. So this is right, num intervals plus n. That's when we can get it again. I'm going to actually make this the top element. So that's when we can add it again. Then it's the letter that we can add, and then it's the current count. So if we're given a -3, how do we turn this into a +2, right? First, we can make this a +2. Or a +3, because it was -3, we add a negative sign in front, now it's +3, and then just -1 from that. So this is what we need to do. One thing we need to check, though, is if there is a number to begin with. So if not max heap, we continue. Otherwise, we go down and pop the top element from the max heap, and what we can do is if count is equal to 1, well, -1, we'll just delete tasks left letter. We actually don't need to even, well, no, yeah, we do need to store the max heap. So what we can do is we say the count, we'll set our tasks left for this letter is equal to negative of this count. If tasks left letter is equal 1, we delete this because that means we have, we'll subtract from this in a second. Well, we can just do that here. So task left count, so that if this was -3, this turns into a 3, and then we minus 1. So if it's 0, we delete it. Otherwise, we've already decremented the count, and this will be just the task left of letter, the negative of that. Well, no, we just add it to the queue. Now, before, the first thing we want to do is pop the double ended queue if it exists. So if dq and dq -1, because what we're doing is we're adding it to the left of the top one. If -1 0 is equal to the number of intervals, what we can do is pop that, or add it to the heap queue.heap push. Well, first we want to take the we don't need this, we want the letter and the count is equal to double ended queue dot pop, and then we want to push onto the heap the count and the letter. But since this is a max heap, we want the negative of count. And then we go to we go through n, but for every letter we do have to push it onto the stack. But since there's only 26 letters, it's log 26, and that's minimal, so it still goes back to oven. So let's see. If the double-ended queue is available, we should actually do this first. So the first index we would have is 1. Yeah, the first interval is 1. And then we add, yeah, that should work. So then, count letter. Okay. All right. Let me go through this and make sure This needs to be the max heap that we're pushing onto, and this needs to be a tuple. Alani. Hey.
She loves. She loves daddy.
Alani.
She's your co-host.
Yes, my co-host. She's cute. Alright, so then we subtract equal 1 and we append left the number of intervals letter and the count. Yeah. And then that would be 1. This would be at 3. And then we loop again for position 2. We don't do anything max heap. We pop from the max heap, which is B. And B is at 2. So now it should be Alani. Yeah, 0, 1, 2, 3, 4, 5. And so we add A here, and then it shouldn't be back until 3. We add B here, it shouldn't be back until 4. So the second position, 2, if not max heap, that'll be true. This is X, and then we get to 3. That'll be the letter, and we push this onto the heap. That makes sense. A negative of the count, and then the letter. And then we continue. Max heap exists now, so that's good. If it exists, we pop the letter, and then we minus equals it 1. Minus equal 1, and then we pop it again, and we will now make this 6 and 7. We add it to 6, and then it should be B. So why is it messing up? Where am I messing this up? Because it's while tasks left. Only equals out if it's 0. Is it miscounting these? No, I know it's not. Yeah, I mean, obviously it's not going to miscount that. Yeah, so that makes sense. All that follows. And then all that follows. That's fine. But then -1. Oh wait, let me. Yeah, I mean that's all gonna match, right? And then we pop it. Yeah, -2a. Then we pop this. We'll have the letter. Yeah, so that makes sense. And then we minus equal 1 from task left. Yeah, why is this? It doesn't make sense. So what I'm saying is this should be, there we go. Okay. Off by 1 error. We love that.
Oh, she's coming back for more to go.
Hey, Lonnie.
She wants to go.
The cat is back.
She's your most diligent student.
Yes. Look, she just rubs against the side.
She's the sweetest girl in the whole wide world. It's a Lonnie girl. Just a tiny.
That one's a little bit of a difficult one. is it messing up? Where am I messing this up? Because while the task is left, only equals that at 0. Is it miscounting these? No, I know it's not. Alright, let's go to the next one. That did not go how I wanted it to go. Alright, we've got LRU cache. Let's reset this canvas. Design a data structure that follows the constraints of least recently used. So the one that has been used the least. With a positive size capacity. And positive size capacity. The key, return the value of the key if the key exists, otherwise return -1. So that'll be one of our data structures. Okay. Void put, update the value of the key if the key exists, otherwise add the key value pair to the cache. I see trying to no event. Okay, that's fine. So what it's sounding like to me is we need to have right on. Right on the piece of paper. So these get input, that's going to be constant time. Each run an O1 average time complexity, so average. We're told that the capacity will be 30,000. Long base 2 of I mean 11. That's basically O of 1, right? So since we know that there's only so what I'm thinking of is having a dictionary that stores these keys, right? And the count of these keys. And then I'm thinking we have a heap that shows us the number of times it's been used, right? And the operation to add to a heap would be this. That equals about 11. Sometimes it'll be less, sometimes it'll be more. That is equivalently O of 1 to me. And I don't know that there would be another way to do this. With positive size capacity. I don't understand what it means by positive size capacity. So LRU cache 2. That means all right, so we're going to have a cache of up to 2 elements. So let me make sure I understand this before. So we have 2 elements. And do you see Alani?
Yeah.
I've got an Alani cam.
I know, I saw that. What do you think she looks at?
My mouse. Because it mimics my screen. So look. Since it's recording my screen, she sees the cursor.
Oh. Jacob, do you have your YouTube on your resume?
No.
You should put it on your resume.
No, not yet.
Why? People can see you grinding away.
Yeah, I feel stupid most of the time, dude.
No, I can understand.
Like I've been struggling. So cache 1 1. This cache 2 2. Key was 2. Evix 2 cache is 1. Okay, so I see. So the cache is only the number of elements that we have, right? Oh my goodness, Alani, don't do that. She was stretching about to go right on my screen. Oh, there she goes. Onto the computer. See, I'm chilling as long as she doesn't turn it off. Like she did last time. I think she'll be fine. Alright. So, already cache size 2. So that means the cache itself is not going to be a set. I mean, I want to say it's a heap, but it's like... I mean, we're just going to say self dot capacity is equal to capacity. I think that's all I need. And then we have a self dot... we'll have a min heap that keeps track of... Well, no. Key was 2 of X, key 2 of caches. Yeah, dude, I feel like I'm just like not getting it, not clicking. It's like got me worried about this interview, dude. So I'm thinking of doing a min heap, but how do we know it's the least frequently used? Because it's not just the frequency, it's the one that's not used. Been not used. We could just have a data structure where this is, let's say, our element 0, 1, 2. Whatever's at this position is the one that's been used the least. So let's say we add A, add B. If we use something, can we just add it to the front? If we use a double-ended queue, we could just pop it and go to the left, right? And then just return this. Yeah, let's do that. So let's say self dot dq is equal to then self dot capacity is equal to 2, or capacity. And then our get is, well, put is this. So self dot dq dot append left, because the pop and add left, they're going to be the same. So our pin left will be return 3, because we also need the value, right? So we could have a double-ended queue to keep track of where we put the key, and then we can also have a self dot map, and that can just be a dictionary. So we would say self dot map key is equal to value, and then we would say if self dot length, we can just say is 0, right? And we can just keep track of this. So self dot length if self dot length is equal to self dot capacity. We're at capacity, and what we need to do is we'll add all of this to the end. What we can do so if we're at capacity, what we would do is we want to pop the key to the right. So least recently used was LRU key is equal to double-ended queue dot pop, and we're popping from the right. And then what we do is delete self dot map LRU key, and we subtract self dot length minus equals 1. Otherwise, and then we append left the key. And then to get something, we just return self.map, and then it would be self.double-ended queue negative. Yeah, we just have this map, self.map key if, well, yeah, all we got to do is return self.map.get key or -1. That part's easy. And then, yeah, so that should be all that we have to do. Least recently used will be the key on the far right. So we'll have a map of the values that exist, and if that exists, we'll just return that key. And when we add a value, we add that key and value, and we append left the key, we add 1 to the length. If it's already at capacity, we pop the rightmost, because that's the least recently used. Delete that from, yeah. This looks good to me. So am I missing something on the dot get return 1? Okay, so if we do dot get, what we do is but see, that's where the challenging part is. I missed that. So this moves it back to the end. This is our way of tracking. Negative 1. Otherwise it is in self.map, and we don't know that current position, right? So because what it would be, yeah, dang, dude. I mean, this is the brute force way to do it. Yeah, that sucks. Shoot. So we could have a, I mean, yeah, the min heap starting to make sense. Dang, dude. A linked list? I guess it does make sense. Yeah, because it would allow us to do the swap right away. And if we had, yeah, I mean, yeah, I would have never got that self dot. Well, I guess this node. So this would just be initializing our list node. And then so now we have we'll just call this one. So what? Cur.next is equal to list node. Cur is equal 1. Cur is equal to cur.next. Sorry, no. This is 0. We add this one. That's the first iteration. Then start the second iteration. Yeah, cur.next is equal to 1. Does it this loop, and then the end of this one we set current to be here. Then we do this, and then we set okay, yeah. And then so from here we would say Why did that stop randomly? There we go. Just randomly stopped working. Alright. Self.root.next is equal to our new list node. And then what we say, so this is adding this off that previous. what we can do is just map, and we can do the key equal to our new node. Dude, I feel like I'm getting destroyed on the Leetcode problems. Makes me mad. And I feel like the ones I'm doing aren't even going to be asked. I don't know. problems, some of them are kicking my butt. Daily temperatures. Let's see. Given an array of integers, temperatures represent the daily temperatures. Return an array answer such that answer I is the number of days you have to wait after the ith day to get a warmer temperature. If there is no future day for which this is possible, keep the answer I equals 0 instead. So we've got temperatures. I'm just going to draw this out so we can visualize this. So we've got these temperatures 75, 71, 69, 72. Wonder if this like feels better if I use this mouse. I bet it does. 72. 76, 73. So we've got these temperatures and we've got an output 1, 2, 3, 4, 5, 6, 7, 8. 3, 4, 5, 6, 7, 8. So yeah, the output will be, we'll have 1 for each day, and it looks like we're going to initialize all these to 0 in this output array. And it says, return an array answer such that answer I is the number of days you have to wait until the after the ith day to get a warmer temperature. So here is day 1 or I, and how many days after I do we have to wait to get an increased temperature? Well, in this case, it's just 1 day. So we would set this to 1. And then what about from this position? Second day. This is also just a 1. What about from 75? It's 1, 2, 3, 4. It's 4 days. 4 days. From 71, it's 2 days. From 69, it's 1 day. From 72, it's 1 day. From 76, it's 0 and 0. So output is 1142, 1100. So based on what this, like just how I walked through this, this is pretty self-explanatory on what the brute force is. The brute force method would be 2 for loops. We would go through each position and loop through the remaining until we find a number greater than this. And we would do that for each position. If we're counting the output array as part of space complexity, then the space complexity would be O of n. If it's not counted as part of the space complexity, it would just be O of 1. So that brute force way is O of n squared, and O of 1 is space complexity. I'm assuming we don't have to count the output. But can we do better than this? Can we do better? So, what I'm thinking is we could probably do a dictionary that we could use to store these values. So again, we have this initialized to 0. It doesn't matter what we initialize it to unless we're using a dynamic programming solution. I don't think I need to use a dynamic programming solution, but it's something to consider. But basically, I could go, maybe I could. Yeah, what if we set, so we know this one will always be 0. The last output will always be 0. And then what about this one? We can check to see, well, I was going to say we could check to see if like 77 is in the answers, but it could be like 81. We don't know the exact number. We don't know the exact number, so is there a way to do it? No, because even if 72, we don't know that 73 is specifically the one that we want. Okay, so let's ignore dynamic programming for a second, because I don't think we're going to be able to do that given that we don't know the exact number that's greater. We start at 73. What if we had some sort of I'm just walking through my options. What if we had a stack and we put 73 on the bottom, and we know this is position 0, right? And we somehow keep track of the position and the output. And we go, and what we do is we say while this 74 is greater than the thing on the stack, we pop it. So 73 is greater than this, and we subtract this position of 1 minus 0, and that would be 1. And then we add 74 to the stack. At position 1. And then we get to 75. And while 75 is greater than the thing on top of the stack, we add 1 here. And then we add 75. While 71 is greater than 75, that's not the case. We add 71. So this is 2, this is 3. And then we go to 69. We add 69 onto the stack. Position 4, 5, 6, 7. And then we get to 72. And while 72 is greater than all of these, we do 5 minus 72. So position 4 would be this 5 minus 4, 1. This, then we pop this from the stack. And then 71 would be 5 minus 3 is 2. Pop that from the stack. Oh, sorry, this position is still 0. This would be 2, this would be 1. And then we add 72 to the stack. And then while 76 is greater, yeah, okay, that'll work. And what that would be is an O of n solution. Because we would be adding these things to the stack, and like let's say all of these were decreasing, and then the last one's incrementing. All of these would be on the stack, and then we would pop all of these and append it. So like technically that's like 2n, but it's still O of n time complexity. We would have O of n space complexity for the stack. It potentially holds all of these elements, and yeah, basically what we do is if there's still stuff on the stack at the end of this loop, we would just loop through while the stack exists, and then, well, actually no, it doesn't matter because we'll default these to be 0. Yeah, that should work. So it'd be O of n time complexity and O of n space complexity. All right, so let's code this up. So one thing we'll have is our output, or we could call it days until warmer. And we'll initialize all of these to 0. And then we'll also have a stack. Okay, so our stack will be initially nothing, and then we'll go through each position in temperatures. And the index will be useful, so I'll have I and temp and enumerate temperatures. And all that I'm going to do is I'll have a while statement. So while stack and this temp is greater than, because it's not greater than or equal to, it's warmer. So while this temp is greater than the top of the stack, and in the stack I'm going to hold the temperature and the value. So the first element of that tuple. While this is true, what we're going to do is say that our prev position and prev, well, yeah, we're going to have underscore for the temp, and previous index is equal to stack dot pop. And then all we do is set days until warmer for this previous index. We set that equal to our current index minus previous index. Awesome. And we keep doing that and setting those positions. And then once we've gone through all of that, we add the current position to the stack. So stack.append, we want the temperature and then the index. And then we would return the days until warmer. So what happens if these are continuously decreasing? All of these would be initialized to 0, and this would return the correct answer. What happens if they're continuously increasing? All of the, I'm just thinking through some edge cases right now. All of these values would be popped from the stack each time, and then the last value would be on the stack. And since the last value will always be 0, that's fine. Everything else would be 1. So yeah, as we see, the last position will always be 1 no matter what. Oh, Alani, you're still in my computer. I didn't notice that. Yeah, and so temperature, days until warmer, stack, that's right, temperatures, temp, it's greater than that first position on stack, that's what we add here. This looks good for me, I think. I'm trying to think of all of the possible situations. If we have no temperatures, this would just return an empty stack. If there's only one temperature, we would just append it to the stack and it would be 0. You have enumerate, that's good. Select that pop. This needs to be a tuple. This looks good to me though. All these test cases are accepted. This would be O of n time complexity, O of n space complexity, and as we can see, we get the output that we were expecting. Awesome. That's interesting. Not doing it that way. Let's do house robber next. You're a professional robber planning to rob houses along a street. Each house has a certain amount of money stashed. The only constraint stopping you from robbing each of them is that adjacent houses have 2 security systems connected that will automatically contact police if 2 adjacent houses were broken into on the same. Give an integer array nums representing the amount of money of each house for the maximum amount of money you can rob. Okay, so we have numbers representing the cash amount. So we have 1, 2, 3, and 1. And we want to know, we can't do adjacent houses. So like these 2 we can't do. So it's either we do 1 or we do 3. And intuitively it makes sense to, well, I think just be greedy, get as much of these as you can. So this looks like it's either 3 or it's 4. Because skipping 1, like let's say if we start at 1 and then we skip to this other one, that doesn't make any sense. Let's say there was a 4 here. If we skipped 1 all the way to 4, that would be 5. But if we just did this bounce, that would be 7. Right? And if we did here, that would only be 4. If we skip that, it would be 7. Either way, this is the same. What happens if it's 11 right here? I could choose to skip it. So it's looking like it. We just want to hit every single position possible, because if we skip one, it doesn't make sense, because the next one it would just make sense. Like it seems like the odd or even one will get it. So it seems we have 2 options. Like, okay, let's look here. It's either start at 1, and that's 3, 7. So starting at 1 is 7, or starting at 3 is 4, 16. 12. Yeah, if we start, it's either 11. Yeah, so it's seeming we either start at 1 or we start at 3. Right? Let me find a counter example. So like, let's say we started at 4. Would we want to choose this 2 and then this 1? That would be 7. Or we could choose just this other 4. That would be 8. Okay, can we do better than 8? 1, so that's 7. Okay, so my hypothesis was wrong. So we do have the option either getting this next one or this one. But these are the only 2 that we really have to consider. Because anything else would just, like if we just skipped all the way to this one, it would make more sense to go to this 2 and then to this 1. Okay, yeah, so we just have 2 options. Either skip the adjacent one or skip the 2 adjacent ones. So it'll be comparing these values. And this looks like a classic dynamic programming problem. We don't even need to. We could add what? I mean, we could add 3 extra spaces here that are just 0 if we wanted to start at this 1. That's the easy way to do it. We're going to use the maximum of these two. But we know these will always be 0, so do we even need to check those? I don't think so. So if we started at 2, we either have the option of 1 or 0. And we want to be greedy and choose the maximum value for each. So we can just have this 1 starting 0. And well, I'm going to want these positions start too. Let's just add 3 zeros to the end of the but we're actually only keeping track of 2 variables. Like, I'm comparing these two, and then when I go to this 4, this next position, okay, so, well, the brute force way that we could do this, I'm jumping into the dynamic programming solution pretty quickly, but what we could do is have a we could have a recursive call starting at 4, and from 4, what we could do is look for the best next position from this place. And we could go through all of these, selecting each of these as the next, but based on my logic earlier, we wouldn't need to do that. So we either choose this one or this one. And then we call it again from this way. This would essentially be O of n squared solution. Space complexity would be O of 1 because I'm not having to store anything, but very inefficient. My dynamic programming solution that I'm proposing, it would just be O of n time complexity because we would iterate backwards through the array once. Now it would be O of n space complexity because we would have the value at each of these positions stored. So for me, the more time efficient solution is normally the better solution. And I mean, obviously that depends on the business needs, but I'd like to go with this solution. The key hindrance here is the space complexity. Now, another thing you can probably do is, since we're only comparing 2 values, we could probably just store these into like two options, like option 1 and option 2. But that's a little bit more complex, but that's something I could probably improve upon once I get this first answer. So I'm going to have a dynamic programming array, and I'm going to initialize it to be length of nums. So if nums are here, then that means we have zeros for all here. And then I'm just going to add 3 to handle these cases, which we could also eliminate this, but it's only 3. I'm just going to do it. So dynamic program is equal to this times length nums plus 3. And then we would just have a reverse for loop. So for I in range length -1, -1, -1. And we set the current position of I to be equal to the maximum of I plus 2 and I plus 3. And then at the end we'll have 2 options between this first position or second, and so we'll return the maximum of those 2 positions. Now, one thing that I have to do here is make sure I'm adding the current position. So nums I, because for each spot that we go, we need to add the position of the current. And so what would that look like here? So if we had just this array and we added these zeros here, we would say this position would be I could decrease on time complexity if I just use this number list as our dynamic programming position. So if I'm allowed to use this numbers list, that changes my method of doing this a little bit more. Basically, I wouldn't need to initialize this. I could just use the existing. So I'm going to implement first using this extra space, and then we can go down. So we start at this position. It's 1 plus the maximum of these, so this is still 1. Then we go to 4. It's 1 plus the maximum of these. This is still 4. Then we go to 2. It's 1 plus the maximum of these. So now this would be 3. And then we go to 1 plus the maximum of 4 and 1. This would now be 5. And then we go to 4 plus the maximum of 3 and 4. And this would be 8. And that matches what we determined as being the best possible answer given my example input. Right, because we skipped this. That makes sense. All right, so this initializes it correctly. This looks good to me. Of time complexity, of space complexity. Let me assume I can use nums, and let's just use that and see if I can do that. So what we can do is just set nums I, and it would be plus equals the maximum of these two. And basically, if these positions are going to be out of bounds, so if I'm going to have a variable length nums is equal to the length of nums, because I don't want to keep calculating this. So this would be if I is if I plus 2 is less than nums, else 0. And we could do the same here. And then we would just return the maximum of, what's the maximum length? Okay, so if length nums is less than or equal to 1, we just return. So it says 1 is the minimum length. So if it's equal to 1, then we'll just return nums of 1, or sorry, 0. Otherwise, we go through this and we return the maximum of nums 0 and nums 1. So this involves me modifying the numbers input array. I did mention we could probably have 2 variables and just store the output using that. Yeah, Sorry, this should be nums. This passes, and this would be O of n time complexity, O of n space complexity, because I'm reusing the input that they give me. Now let's use this just using variables. Psi plus equals maximum of first and second. So this would be initialized to 0. These first couple ones would still be just 1, 1. But this is if we're not modifying. Oh yeah, we don't even want to modify the array, so this would be we could go until